Hello, my name is Montgomery Colbeck, and today I'm going to be talking about a proposal to upgrade the IPv4 network to utilize the full gigabit cabling and all of its capabilities, as well as upgrade it to IPv6. So, the first thing I'm going to do is do a basic network overview of what's going on. We have gigabit connections that connect all of the switches to all other devices. We have serial connections that act as the connections between strictly router to router. Then we've got your basic hosts, your routers, and your switches. I plan on going into more detail about each one of these devices further in the presentation. This is the East Coast network. It is the larger of the two networks. It utilizes 8 subnets, each with a different amount of hosts in them. There are 8 switches, 4 of which are 10.100.1000, and 4 of which are 10.100. There are 6 routers, and 3 of them are 10.100, and 2 of them are 10.100.1000, and 1 is the Cisco 2900, which is capable of 10.100.1000 as well. So I want to go more into depth about the East Coast network basic connections. We have our serial connections, which are strictly router-to-router connections. The reason that serial connections are used is because historically, serial connections have always been associated with routers, and most routers today still have serial connection ports for the sole reason that it works well. There is no need for an Ethernet connection between a router because Ethernet has an abundance of different configuration standards and different abilities that can severely mess up a network. In essence, people use serial connections between routers because it takes a little bit of complication out of something that is already massively complicated. Serial connections are simple, and routers don't need the level of complexity that switches do when it comes to cabling. They also reduces overhead on the network, like I said, because there's less to it. Next, we want to talk about our gigabit connections. Gigabit can also be expressed as 10, 100, 1000, which means 10 megabits, 100 megabits, or 1000 megabits. We want to utilize this cabling to its maximum potential. But as you can see, based on what I said earlier, there are devices on this network that are causing bottlenecking and will cause network congestion. So I'm going to start off in the beginning and work my way throughout the network. And the first thing that we see are the hosts. What is a host? A host is something that people use to interact with the network. Typically, it is the employees or the end users that are using these hosts in order to interact with it. The purpose of them is to allow other employees to be able to communicate with other networks, other people on the network, and be able to transmit information effectively. Another way to look at hosts is as the access layer to the network, if you want to think of it in terms of topology. Next, I'll talk about the switches. It is important to know the difference between a 10100 and a 10-100-1000 switch. 10-100 is only capable of speeds of 10 or 100 megabits, while 10-100-1000 is capable of 10, 100, or 1000 megabits. These speeds are usually automatically assigned by the router based on the configurations. This is built into the iOS image to automatically detect which speed it should use. In this case, we've got half and half. So it is causing severe network congestion because half of the networking devices aren't capable of actually using the full capability of the wiring. Another thing to notice is how the host allocation is based on the actual switch that is being used, because the 10, 100, 1000 switches are actually allocated to the subnets with the most hosts, which will also give the most overhead. So it is actually intelligent of the designer to make sure that the switches that are capable of handling more speeds are actually handling the subnets that will have the most networking traffic. And the other 4 10-100s are used on the 4 smallest hosts. Next, we've got the East Coast routers. What is the difference between a 10-100 and a 10-100-1000 router? Well, the difference is exactly the same as switches. The same concept applies to this device. A 10-100-1000 is capable of 10, 100, or 1000 megabits, while a 10-100 is only capable of 10 and 100 megabits. So half of the routers essentially are causing network congestion, assuming that the serial links are capable of gigabit speed, which is not specified, but I am going to assume that they are for the essence of this project. Another thing to note is that there is a gateway at the end, and it's a different router. This is a Cisco 2900 router. And before I get into that, I want to tell you what a gateway is. A gateway is the gate to the internet and other networks. It allows you to take information from your network and take it somewhere else. A gateway is your voice to the rest of the world, essentially. The reason that this is different is, well, the actual reason is it's not necessarily too different. There is no necessity to have the 2900 versus another 1941 router, because the 2900 does make a good gateway because it comes with a lot of bells and whistles that the other two routers don't have. For example, it is modular, as in it comes with the ability to have aftermarket upgrades installed into it to make it better. But in the end, it still does the same job as the Cisco 1941. It routes information, but this one has a little bit more responsibility. Now, I'm going to get into the West Coast network. I will spend a little less time on this simply because it's virtually the same networks. It follows all the same concepts, and it has all the same hardware. It's just a little bit smaller. It uses the same cabling types. The network is pretty much exactly like the other one, the only main difference being that there's smaller subnets and there are less of the subnets. Also, the gateway router is a 1941 rather than a 2900, so it's a little cheaper in that sense. Now, on to the proposal. Why do we need IPv6? So why do we want it, and why does it even exist? It exists because IPv4 is running out of IP addresses. Very soon, in my lifetime, and probably in yours, we will see the end of IPv4 because it will have been completely exhausted of IP addresses. This is why IPv6 was introduced. IPv6 has 128 bits versus 32. The first 64 bits are known as the prefix. You can get your global prefix, and then you can get your subnet, all in that first 64 bits. After that, you have to allocate your host. So the next 64 bits typically are used for host. And as you can imagine, that is a tremendous amount of hosts, because think of the amount of hosts we get with 32 bits on IPv4, and we don't even use all 32 for hosts. It truly is an astronomical number. So why do we need this if it's already subnetted and working fine? Well, if we want a 25% increase in each of our subnets, we can't do that with IPv4. But we can do that with IPv6 because there is such an astronomical number of IP addresses per IPv6 subnet. It allows for much more than 25% growth, actually. So, I know this is small, but this is how I've IPv6 subnetted the East Coast network. I'm just going to read off the prefix that I used and explain why I used it. We have the hexadecimal digits as well in IPv6. Instead of just 0 through 9, we have 0 through 9 and A through F with hex. So the prefix I used is 2004:04D/AC32:0001:/64. And that 0001, that's the subnet. It's the same thing as the subnet in IPv4. It's the same concept. It increments. So I just incremented it for each subnet that I needed. And I put a subnet in between every connection because that is what the instructions specified. I did the same thing for the IPv6 West Coast network. I will also read off the prefix just for the sake of elaborating. We have AD45:1234:67F2:0001:/64, and then I also incremented it for each connection. So, what do we need to upgrade to IPv6? Well, we need to upgrade the switches and the routers. The hosts don't really need upgrades. The two switches that are already used, the 10.100.1000 and the 10.100.1000 router, they are capable of IPv6 already, which is good for us, since that means we just need to replace the 10.100 devices with 10.100.1000 devices. So, how much is this going to cost? So, according to serversupply.com and Amazon, I can get the same router, the Cisco 1941, for $600 each. That will need 3 of them for the East Coast network, and that will be a total of $1,800. we need a total of 4 switches for the East Coast, and according to Amazon, that is $200 each. So that's going to bring the total up to $2,600 for the East Coast network. Now, the West Coast network is going to be a little cheaper because we only need 2 routers and 3 switches. That'll be a total of $1,200 for routers and $600 for switches. The total is going to be $1,800 for the West Coast network. Now, to conclude, I want to reiterate why IPv6 is important. And it's important because every business eventually is going to be using it. It's going to be good to get familiar with these concepts now versus later. If we're already on the IPv6 train, we won't need to worry about it when everyone is scrambling to transition. And bottlenecking is bad. This is the main reason that we wanted to upgrade this network, because you're not utilizing your hardware properly. If you have cabling that's capable of speeds faster than what your hardware actually can handle, you're wasting money, you're wasting resources. So this new network, it should perform pretty well. There should be no bottlenecking considering everything now can handle gigabit speeds. And we can account for pretty much an indefinite amount of subnet growth because of the vast amount of host addresses that are used in IPv6. So that is my proposal for IPv6 upgrading on the West Coast and the East Coast network. Thank you.